Is lesson 12 for year 13 physics, and we're coming towards the end of waves. This one is on the Doppler effect. So what is Doppler effect? So Doppler effect has to do with the apparent change in frequency that is observed by an observer when there is relative motion between a moving source and the observer. So if you have a stationary source that is producing a sound or a wave, it'll go in all directions. However, if the source that is producing the wave is moving forwards, then you'll see that the wave's bunching up in front and spreading out at the back. Okay, so for the stationary source, the wavelength and the frequency is the same at all points. Now let's explain this Doppler effect. It has to do with a moving source that is also producing a sound. Okay, so when a police car, that is the source, with its sirens blaring, so that's your wave, approaches Callista, it's an observer in front, Callista will hear a sound of a higher pitch or higher frequency. Sarah, who's driving the police car, hears the actual frequency because there is no relative motion between Sarah and the sound waves. The reason why Callista hears a sound of higher pitch is because the wave fronts bunch up in front of the police car, making the apparent wavelength shorter. The speed of the sound wave stays the same. Since v equals f lambda, Callista, who's standing in front of the approaching car, will hear a note of a higher pitch or frequency. Now, Olivia is standing on the road behind the police car, and she is going to hear a sound of a lower pitch. This is because the wave front spread out behind the police car. So the apparent wavelength increases. The wave speed stays the same, hence the apparent frequency or pitch will decrease. Now, moving on, this was lesson 12, the Doppler equation. So I will combine both those in this video. So for the source that is approaching, so what happens? So this is derivation of the formula. So for this observer here, the observer is going to hear a different frequency. So that frequency depends on wavelength and wave speed. So frequency is wave speed, which is the same divided by this changed wavelength. For the driver of the car, they are going to hear the actual frequency. So frequency is again the relative wave speed divided by the relative wavelength or the apparent wavelength. So why is it VW minus VS? Because they're both of them moving in the same direction, so the relative speed is the difference between the two. Okay, and there's your apparent wavelength. So the apparent frequency is wavelength divided by this, by the apparent wavelength. The wavelength of the source of the sound divided by the wavelength of the apparent wavelength. So you end up with this formula for the apparent frequency heard when a car or something is approaching you, blaring its siren. Similarly, if the source is going away or receding, it's going to be VW plus VS in the denominator. On your formula sheet, both these are combined into one with plus or minus here, but when you do a questions, you've got to choose whether it's this one or this one, depending on whether it's coming towards you, in which case it's this, or going away from you, in which case it is this. Now there are Doppler graphs. So this is a frequency against position graph, and when the car is, and this is your actual frequency, this is somebody who's standing, and this is something, let's say an ambulance or a police car with its sirens blaring. When it's coming towards you, the person is going to hear a steady higher pitch. When it is right in front of you, the person is going to hear the actual pitch because there's no relative motion for that small amount of time. And when it's receding or going away, you're going to hear a steady lower pitch. However, if the car or whatever it is, the vehicle is accelerating, then it will be an increasing higher pitch, and then it's going to drop down. This is the actual frequency at this time, and then it will be a decreasing pitch when it moves away or accelerates away.